Hello math people, it's Mr. Ray here with our next lesson in grade 12 data management. We are working in the third unit of the course which is called probability distributions. So the first lesson was an introduction into what are these things called probability distributions. We saw examples of where we created tables. It looked like a table of values. Like a function you've seen in previous grades. We also did histograms of the outcomes, probabilities of the different outcomes. And we looked at something called the uniform distribution, where every outcome had the same probability. A little boring, but there's lots of those out there. The next three lessons, the second, third, and fourth of this unit, we're looking at very specific distributions. They're all kind of related to each other. Today we're going to look at the binomial distribution, and then we're going to look in lesson 3 and 4 at the geometric and hypergeometric distributions. Now, the binomial distribution, it's probably number 2 on the hit charts of probability distributions in terms of usefulness or applications. The most famous distribution, probability distribution, is the normal distribution. We're going to save that for later in the course, the last unit. There's a lot of stuff we can do with that, so it's got its own unit. So we're just going to look at binomial distribution today and follow that up with the geometric and hypergeometric to finish the unit. So a couple definitions from previously. Probability distributions, it just lists all the probabilities of all the outcomes. You could do that in a table of values or in a histogram, any kind of chart. We also have the random variable capital X, is what we always use, and it basically, we use that as our variable to check if the outcome was a certain value. And today, the binomial distribution. So the official definition, a distribution with independent trials. Okay, so the first key word here is independent. Okay, so if you remember back from the last unit, independent events, basically the probabilities of those have no bearing on anything if you did another trial before or after. So the probabilities remain unchanged regardless of what you just did. So that's important for this. So anytime you use a binomial distribution, it has to be some application where independent trials were used. And what we do is we actually narrow it down to either success or failure. So either you got a certain value or values, or you didn't. And this may sound limiting at first, but it's actually not, because, for example, you could kind of turn the die, rolling a die trial into a binomial distribution if you just wanted to see if the probability of getting an even number, 2, 4, or 6, when you roll the die. So you could basically label getting a 2, 4, or 6 as a success, and anything else, a 1, 3, or 5, would be a failure. So you can kind of group the outcomes into success or failure that way. Okay. We're also introducing expected value. We talked about this in the last lesson. So this will be a formula just for binomial distributions. We'll come up with a brand new one. Okay. Now we've got some key concepts here. I'm going to just talk about these in more detail. It's kind of what we want to do is actually kind of discover this as we do our examples, and we'll come back to this and just summarize the lesson once we've done some examples. So let's do that now. Okay, so the first example, counting success. So again, we're back to the 2 dice. We're going to roll the pair of dice 5 times, And we want to know what the probability that we get doubles twice, exactly twice, out of the 5 times, okay? So, first thing we notice, the 2 dice are rolled 5 times, so that's your number of trials. So, in terms of how to use this will be the value n. We've seen this lots of times in the past already. Okay, and occurring twice. Well, that's going to be important in a few seconds. So, what's the probability that doubles occur twice? Well, the first thing we have to do is, what's the probability of rolling a pair of dice and getting doubles? Well, I'm not going to redraw the whole 6x6 chart. Basically, you've got 36 outcomes when you roll 2 die. So you can easily see that, well, I could get double 1s, double 2s, doubles 3s, up to double 6s. So there's actually 6 ways you can get doubles out of 36. Okay, so we'll start with that. The probability of rolling doubles once is 6/36, or reduce that to 1/6. Okay. Now, so the probability of rolling doubles, this would be considered a success. Okay, so that if we roll doubles, we'll consider that to be a success, and we have a special variable for the probability of the success. We're going to call that P. So probability of success is 1/6, and we have a brother sister variable that goes with that, Q, and these are both lowercase. Q is the probability of failure, and these two are always related, because if we add P and Q together, we get 1. So we can easily, if we know one of these, we can get the other just by subtracting it from 1. So the probability of not getting a double, or the failure in this example, would be 5/6. Okay, so I'm going to start here. Probability of rolling doubles, and again, that's our success. You don't have to write this every time. I'm just trying to. So I'm just going to write this as 1/6, and the probability of failure, which in this case is not rolling doubles, that's 5/6. Okay, and we're going to use our random variable, discrete variable, is x. So x will be equal to the number of doubles rolled. So that 2 came from here. Sorry, no. Well, we want it to be, we want x to be 2, but so we're going to use 2 for our value of x in a second. Number of doubles rolled. So here we go. So I'm going to start off with probability, and I'm going to use my random variable x, and x represents the number of doubles rolled, so we want that to be 2. So the probability that x equals 2, and I prefer you write it this way instead of just p bracket 2, because this shows that it's related to that very directly. Okay, that's going to be equal to, now, if, just as a side note here, if you roll doubles twice, that means you don't roll doubles 3 times. So if I just look at the probabilities of those 5 rolls, well, twice I'm going to have 1/6 as my probability, and 3 times I'm going to have 5/6. And when because this is, this is the AND situation, we're going to be multiplying. So you would think, okay, I could write that out and just multiply these all together, and that would be my answer. But we're leaving something out if we do it that way, because we have to consider all the different combinations of rolling two doubles and 3 non-doubles. Okay, and that could occur like this, but it could also occur 5, 6, 1, 6, 5, 6, 1, 6, 5, 6, and all the different combinations that come with that. So luckily, we've already learned how to do this in Unit 1. So I want to know all the ways of arranging this first, and then I'm going to multiply it by this probability, this product of probabilities. So if I want to know the number of ways of arranging these 5, well, I could focus on the 2 successes. So out of the 5, I want to choose 2. So this would be 5 choose 2, and that's going to be equal to 10. That's our normal combination. So there's actually 10 ways that I could arrange these in a distinct order. Okay. That's going to be multiplied by this whole thing here. Now I don't really want to have this is a bit of a mess, especially once you get to something with a higher number here. So I'm going to do this as powers. So I know I'm going to start off with the basically my p-value, my probability of success, and that's being multiplied by 2 times here, which happens to be the number that's associated that's here. So these 2 numbers will always be the same. And then we also multiply by 5, 6, 3 times, and you notice that these 2 numbers will always add up to our n number, the number of trials. So now it's just a matter of multiplying this out. So like I said before, 5 choose 2 is 10, and then I've got I could do this as fractions multiplying, but I prefer to well, in this case 1 squared is just 1, and then 5 cubed on the top, and then on the bottom I've got 6 squared, 6 cubed, that's 6 to the power 5. So if I'm doing it on a calculator that doesn't have fraction abilities, that's what I'm going to do. So I multiply this all out, and I get approximately 0.1608. So therefore, the probability of rolling 2 doubles in five trials, 5 different rolls, is that number. I could say 16.08%, or just leave it as a decimal. I definitely would not want to leave it as a fraction. That would be too complicated. Okay, so we've actually developed our formula here, sort of without knowing the formula. So if I actually go back, you can see the generic formula on the first page. So the probability of x is equal to, and then we have our combination here, and it's n choose x. So remember, x is the number that you want your random variable to be. So that was 2 sets of doubles. So our example is n equals 5, x equals 2. Remember, p was 1/6, that was success. Q was, so it did work out to be the same as this. 5 choose 2, 1/6 to the power 2 times 5/6 to the power 3. So that is our probability distribution formula that we're going to be using. Okay. Let's go down to our next example. So this has lots of questions related to it. A random number generator provides a number between 1 and 100 over a total of 5 trials. Okay, with repetition permitted. So what that means is, say the random number generator picked a 25 as our first number. Well, it can still pick 25 again. It's not taken out from the choices of the subsequent rolls. So it's basically, you could call this with replacement. So once you've chosen a number, you basically put it back to be possibly picked again. Okay. Calculate a probability distribution for the number of times a prime number is output. Okay, so we're going to have to figure out how many prime numbers there are. So then we're going to identify the discrete random variable, calculate the probability distribution. So we'll do that for the first time, and double check that the sum equals 1, which it should, because We've seen probability distributions. The sum of the probabilities always has to equal 1. Graph the probability distribution. We use that histogram, and then a couple of questions which we'll look at when we get there. Okay, so the very first thing, part A, was identify the discrete random variables. So we're going to use our old friend capital X. So what are we actually counting here? We're counting how many times a prime number was picked when a random number was picked between 1 and 100. So X is going to represent the number of times a prime number was chosen. Now, we also know we're going to do this 5 times. We're going to pick 5 numbers. We don't have to say that here, okay? You don't have to get that detailed with X about how many times you're actually running the trial for. That does not need to be included. Now we're going to calculate the probability distribution. So there's a lot of work we have to do before we get there. First of all, we have to know how many prime numbers are there between 1 and 100. And I will tell you the number, and then I will actually list them, just in case you doubt me. There are 25 prime numbers between 1 and 100. So let's think about those. Remember, prime numbers are numbers that have no factors. One and the number don't count as factors. So let's start our list here. So we got 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47. So you notice I'm skipping some numbers, obviously, because they're not prime numbers, like 45. Any number that ends with 0, 5 obviously is not. Any even number is not. And then you got to think of things like 49. I mean, that's 7 times 7. So next one would be 51, 53, 59, 61, 63, 67, 69 is not, 71, 73, 77, 79, 81 is not, 83 is, 87 is not, it can be divided by 3, 89, and then 97, all the other 90s are factor numbers or non-prime numbers. So if you count these up, just trust me, that should be 25. If it's not, I apologize. The correct answer is 25. So now I'm going to do what we did in the last lesson. We're going to do our distribution table, probability distribution. So in the first column, we've got number of primes, and that's our random variable X. Then we have our probability of getting and I'm also going to include at the end, once I do this part. So this part here is your probability distribution. I'm going to include the X times PX, and that's going to help me calculate our expected value. So to start with, how many primes could we get if we ran this random number generated 5 times? Well, they could all be 5. Sorry, they could all be prime. So that's 5, or none of them could be 5, and that would be 0. So, and anything in between would be fair game, because you could pick anywhere from 0 to 5 prime numbers. So what we do, you always have to include all the possible outcomes of this experiment. You could have up from 0 to 5 prime numbers selected. And for each of these, we're going to calculate the probability of getting that number of primes. Okay, so this is where we're going to use our formula for our binomial distribution. So if I'm choosing, so once you've got the first one, the next ones become quite a bit easier because there's a real pattern to this. So the first probability, I'm going to remember our n value in this case. Maybe I'll put them up here. So n is equal to 5. What value did we use for that? I guess it would be little x. I'm going to call it r. So the number of primes that we are checking for, oh, actually that's going to be this number here. So forget that. But we also need our little p and little q for the probability. So we haven't done that yet. So we know that there's 25 prime numbers for the 100 that are here. So that's 25 out of 100. So that reduces to 1/4. So there's a little fact for you. 1/4 of the first 100 numbers are prime numbers. That means that, so the probability of getting a prime number is 1/4, and therefore the probability of not getting a prime number is 3/4. So we need those in our formula here. So we start off, so it's going to be 5, choose, and then we use the number of primes we're looking for. 5, choose 0, and then we have our p, so 1/4 to the power, so if we're finding 0 of these, so this exponent is always going to be the same as our r value, which is going to change from row to row. And then we multiply it by q, which is 3/4, and the number that aren't primes is actually, so if there's 0 primes, that means there's 5 non-primes. Okay, so we're going to calculate that. Now, these can be time consuming, so it's really useful to have a good calculator. I'm just going to put the final decimal, so rounded decimal, 0.2373. This is a pretty shoddy looking table, sorry about that. Now, once we do that one, the rest of them are fairly, well, they're easier to do than the first one once you get rolling here. So now I'm choosing 1. So basically, wherever I had a 0 for this row, I'm changing that to a 1. And this row, sorry, I might as well just do that now. 5, choose 1, because we're choosing one of them to be a prime. So now it's 1/4 to the power of 1, 3/4 to the power. Now, another thing that always has to be true here, these two numbers for any row on this table, these two exponents have to add up to 5 every time, because that's the sum of the numbers. So this would be a 4, because now we're choosing 4 non-primes. That is equal to 0.3955. Okay, and then the rest, 5, choose 2, 1/4 to the power 2, 3/4 to the power 3. Okay, and you notice kind of the pattern here. This is going up. This is always 5, this is going up, this is going up, this is going down. Okay, always sum up to 5, 2 plus 3. That's equal to 0.2638. And then for 3, finding 3 primes from the 5, that's 5, choose 3, 1/4 to the power 3, 3/4 to the power 2. That's equal to where are we? 0.0879. And while we're doing this, you can kind of see what's going on, like which which is most likely to happen here. So you start off with basically a probability of like 24%, 40%, and then it's going down, so 26, 8%. So right away you can see that 1 prime would be the most commonly run experiment out of the 5, and this is rapidly decreasing as we get to 5. So this would be 5, choose 4, 1/4 to the power 4, 3/4 to the power 1. Okay, 4 plus 1 is 5. That's equal to 0.0146, so getting quite low, but 1% of the time that's what happened. And then all 5 of them being prime, 5 choose 5 times 1/4 to the power 5, 3/4 to the power 0, and that is equal to a very small 0.0010. Okay, so that's a probability distribution for this situation. Now, if you added these up, now because we were doing some rounding for the decimals, it doesn't always exactly equal 0, but it should be within a few. So I'm just going to put approximately 1. It might be off by a couple thousandths, but that's just rounding, like I said. Okay, so there's our distribution. I'm going to add this last column here, which we're going to be using to get our expected value. So this is where we multiply the number of primes with its probability. So this is x times p of x. Okay, so 0 times that, obviously 0. 1 times this. 2 times this. 5, 2, 7, 3. 3 times this. 0.2637. 4 times this. 0.0586. 0.005. Okay, and if you sum up this, we actually get, well, even with the rounding, 1.2501. Okay, so we go back to what we were asked here. We identified the discrete random variable, calculate the probability distribution, verifies the sum equals 1. Well, it does. I'm not going to do it separately, but it does. Graph the probability distribution. So I'm going to do that here. So we did do this already in lesson 1. So it should be no brand new thing here. So on the bottom, we put all the possible outcomes, which is from here. So we need to have 0 through 5. And this is your value of x. Let me put that over here. And over here we have the probability. Just let me write sideways for a second. So that's your p of x. Okay, and this is where, to get the scale here for the vertical, we look at, not looking at this one, I'm looking at p of x. So the probability, the highest probability we got was like 0.39. So if I go up to, say, 0.4, and then cut that in half, and this would be 0 here, 0.1, 0.2. Okay, so now it's just a matter of plotting this. So probability of 0 was 2.2375, so that's about up here. So if I do my dotted line, it's about there. Here's my first bar. And then for 1, it'd be 0.3955, so that's basically right at 0.4. Okay, and then for 2, it was like 0.26, so a little bit higher than 0. Okay, and then for 3, 0.08, so that's dropped quite a bit. So that's about here. 4 is 0.0506 around there, so that's about here. And then this one was extremely low. I'll just kind of put a line near the axis to show that there is something there. So that's what the histogram would look like. And this is histograms are great because they give you a nice visual representation. We did talk about the most probable outcome here being getting 1, but it's good to see the relationship between all the values. You can see, the 0 and 2 are pretty close to being the same probability. They're on both sides of 1, but then 3, 4, 5 drops off very sharply. Okay, so that was part C. Graph the probability distribution. What does p x equals 5 tell you? So that would be this line here. So for D, px equals 5 is the probability of selecting 5 prime numbers. And I think what we might be asked here is, is to kind of look at the data and interpret it. Basically, it's very unlikely. So I'll put that here, very unlikely, like it was less than 1%, 0.1%. So you could imagine that if there's only 25 prime numbers and you selected 5 of those 100 numbers randomly, the chance that you're going to get all 5 of them to be prime is very low. Okay, and then E, calculate the expected value and interpret its meaning. So we did it the same way. We did this extra column, x times p of x, and we got 1.2501. But I'm going to share a little secret with you. There's actually a formula for the binomial distribution to get its expected value, and it's a very nice, simple formula. So the expected value is E of x is equal to n times p. So n is the number of trials, p is the probability of success. So I'm going to do it that way. So E of x is equal to np, which is, in our case, n is 5, p is 1/4. So that's 5/4, which is 1.25. And if you notice, these two are, we did have the little rounding issues when we were calculating these, but they're basically the same number. They should be. So a lot easier to calculate the expected value for binomial distribution by using this formula than by doing this column. Okay, but I just wanted to show you that you do get the same thing. Okay. All right, so let's move on to our next example, and we're still in the prime numbers, every mathematician's favorite subject. So slightly different application of it this time. Tan's family moves to an area with different telephone exchange. So a telephone exchange is basically after the area code, say it's 905, the next 3 numbers would be your exchange. So they're moving, they're going to have a different exchange, have to get a new telephone number. I don't think that's true anymore, but this makes a good question. Telephone numbers in the new exchange start with 446, and so it'll be 446 followed by 4 numbers, and it's saying here you have a equal likelihood of getting any of those 4 digits to be anything from 0 to 9. And Tan's favorite numbers, because she loves math, 7. So we want what we want to calculate is the probability distribution for the numbers of these prime numbers in 10's new telephone number. So when we say new telephone number, I just mean the exchange, so the 4 digits after the 446. So we want to calculate the probability of having 0 prime numbers in our phone number, 1 prime number in our phone number, 2, 3, and all of them, 4. So it's a perfect example of this. So again, this is going to be binomial distribution, because like once we choose a number for the first digit, we can reuse that. So it's independent trials, and we're gonna chosen for each digit was a prime. We'll consider that to be a success. If it's not a prime, it's a failure. Okay, so let's do our probability distribution. So we have our 4 prime numbers. They told us what they were, but we knew that from the previous question. 2, 3, 5, 7. So this is out of 10. We do count 0, so basically 0 through 9 is 10 numbers. So the probability of getting a prime number for any digit is going to be 4/10. And I'm going to change it to a decimal this time. So 0.4. And that makes the probability of failure, oops, it's not a G, it's a Q. So remember, P plus Q always equals 1. So once you've got P or Q, you get the other one just by subtracting 1. So that's 0.6. 60% chance the number that it is. So now we do our table. Probability distribution. So we're going to have number of primes, which is our x, random variable x. And remember, we can have 0, 1, 2, 3, or 4 in our telephone number. Okay, and over here we're going to do our P of x. I'm not going to do P of x or x times P of x this time, because we have that shortcut that we can answer part B with. So P of x, let's give ourselves enough room here. Okay. All right, so we're going to use our distribution, our binomial distribution formula. So if I want to know the probability of getting the number of primes to be 0, and remember it's 4 numbers we're choosing, so maybe I could write n equals 4, and I've got my P and Q over here. So to choose 4, it's going to be 4 choose 0, and the probability, so 0.4 to the power, so this would be 0 because that represents success, and we have no successes, and 0.6 to the power 4. This is equal to 0.1296. So basically a 13% likelihood that a random phone number would have no primes. And then for 1, remember how this works. So 4 choose 1, 0.4 to the power 1, 0.6 to the power 3, because 1 plus 3 is 4. 1 prime number, 3 non-prime numbers. And this is equal to 0.3456. Then for 2 prime numbers in the 4 digits would be 4 choose 2, 0.4 to the power 2, 0.6 also to the power 2, and that's equal to 0.3456. It turns out it's exactly the same. Interesting. And then for 3, 4 choose 3, 0.4 to the power 3, 0.6 to the power 1. That is equal to 0.1536. If the probability of getting all four of those numbers prime numbers, this is probably going to be most unlikely for all of these. 4 choose 4, 0.4 to the power 4, 0.6 to the power 0, because no non-primes, and that's equal to 0.0256. So that's like 2.5% compared to close to 35% for 1 or 2 primes. So now if you do add this up, as in all probability distributions, assuming you do your math right, this is going to be approximately equal to 1. And like I said on the last question, the only way it wouldn't be 1 is if you made an error or you just rounded. And sometimes the rounding, even though you do it correctly, will get you, 1/10,000th off in this case, or maybe 2. Okay, so there's our probability distribution, and like I said, you could use this to basically to say that the chance of getting no prime numbers is 0.1296. The chance of getting 3 prime numbers is that. You could also group these together. You could say the chance of getting 3 or more prime numbers, that would include getting 3 and 4. You would just add these two together, and we're going to see questions that have that we're going to use that. Okay, now the second part, what's the expected number of these prime digits in the new telephone number? So if you took a whole bunch of random numbers, and what would be the average or the expected number of prime numbers? So expected number of prime numbers, that's going to be equal to NP. Again, that's our formula, which is equal to, so our N was 4, our probability was 0.4, so that's equal to 0.16. So 16%. Oh, I did that wrong. 1.6. And it's not a percent. It's the expected number of prime numbers in your 4-digit phone number. Okay, and you can kind of see that 1 and 2 are the most popular, so you would expect the value to be somewhere between 1 and 2, and it is. Okay, so that's it for example 3. Let's try the next one, and this is where we kind of group together these values. So the failure rate is 5% in the initial production run of new computer chips. A quality control inspector selects 30 chips for testing. What is the probability that more than 2 of them are defective out of the 30 that you selected, that he or she selected? And then what's the expected number of defective chips? So this is expected value, just like that one. Okay. Now this one's an interesting one because we are trying to find the number of defective chips. So you might think defective, well, that means failure, right? Well, according to the computer chip company, it is. But for our statistics, for our distribution, our success will be the number of failures. I know that sounds kind of backwards, but that's the way it is, because if we say, the probability that X equals 2, that means probably there's 2 defective chips, not that there's 2 good chips. So I'm going to actually write that out here. So the probability of success by our math definition actually means the failure of the chip. So you have to be very careful when you read the questions. Okay, it's easy to mix this up, and then your probability distribution will be upside down because you're saying success is actually the wrong thing. Okay, so in our case, it's already said the failure rate is 5%. So that's because failure is our success, that means our p-value is our failure rate. And I know that sounds a little odd, so I'm going to write that as a decimal. So probability of success, meaning the chip failed, is 0.05. Therefore, the probability of failure, meaning the chip was okay, is 95%, 0.95. So now we're actually going to work this out. So this will be a little different here. So I'm now not saying, like I did on the last question, or at least example 1 and 2, I'm not saying probability x equals 2. We want to know that probability of more than 2 of them being defective. So that basically means probability that x equals 2, or x equals 3, or x equals 4, etc. Okay, so that's a lot of equal statements. So I'm just going to start off by saying probability that x is greater than 2. So more than 2 means that 2 is not, we're not looking for 2, we're looking, sorry, for 3, 4, 5, up to 30. So probability that x is greater than 2. Now, you can see quite easily, this would be a lot of calculations if we had to calculate probability x is 3, and then add that to the probability x is 3. So we actually use instead of looking for 3, 4, 5, 6 up to 30, we're going to do the opposite. Okay, so we're going to find the ones that aren't part of this, and we're going to subtract it from 1 because we know all the probabilities add up to 1. So it's much easier to do this way. It would take you several pages to do it the long way. So I'm going to subtract the probability that x is equal to 1. Sorry, x equals 0 to start with. Okay, and then I'm also going to subtract the probability that x equals 1 and subtract probability x equals 2. Now you notice on this question I didn't do a probability distribution, partly because they didn't ask us to, but mainly because if I did a complete probability distribution, it would consist of 31 rows, basically from 0 to 30. And like I said, we don't need to know all those other values. All we really need to know are these 3. So we're actually going to calculate them inside the formula. Okay, so now I'm going to subtract this probability that x equals 0. So this is where we have to kind of use an applicable formula like this for this question. So remember, our n value, I guess I could put that here, our n is 30 because we're inspecting 30 chips, and we want to know the probability of having 0 failures, 1 failure, and 2 failures out of those 30 chips. So our n value is 30, so it's 30 choose, in this case, 0. And then our p-value, 0.05, and this time it's to the power 0. And then q, 0.95 to the power, and that'd be, 30 minus 0, which is 30. So that's the calculation for p probability x equals 0. And then we do this 2 more times for 1 and 2. So this is now 30 choose 1. 0.05 to the 1, 0.95 to the 29. Remember, this goes down. And then our last one, 30 choose 2. Let's try to squeeze this in, 0.05 to the power 2, because it's whatever that r value is, 0.95 to the power 28. Squeezed it in. Okay, so I'll do this in 3 steps. So I'm going to actually calculate the combination value and the combined probability product here. So this is going to be 30 choose 0 is 1, and the rest of it is 0.2146. And then 30 choose 1, well that's 30. And that product is 0.0113. And then this is where it starts getting bigger. 30 choose 2, that's 45. Sorry, not 45, that's 435. Times 0, this is actually going to be very small, 0.0006. Okay, now I'll just put in one more step here where I multiply these three things before I combine them. So that's 0.2146 minus 0.339 minus 0.26. So I wanted to do it this way just so you see these numbers, because this is the probability that there are no defects, 0 defects in the 30. This is the probability that there's 1 defect in the 30 and 2 defects in the 30. Okay, and if I subtract all three of those from 1, I get 0.1854, which that is the probability that they're we go back to the question, what's the probability more than 2 of them are defective? Therefore, this time I'll put percent, 18.54% chance more than 2 chips are defective. Okay, so it's a lot more math than what we're used to the last couple of units, but it's similar math to what we've done, just more of it. Okay, and hopefully you see the strategy here of subtracting the probabilities we don't want from 1 rather than just add up the probabilities we do want, which would be 28 of them. And I don't want to do this 28 times. I'd much rather do it 3 times, as I'm sure you would. Then part B is what's the expected number of defective chips? And we're going to use our handy formula for this. Expected number of defective chips. That's equal to NP. And remember, N is 30. Our P is 0.05. Multiply that out and get 1.5. So for every random batch of 30 chips, you would expect that 1.5 of them would be defective. Obviously, you're not going to get 0.5 defective, but that you've seen that now several times. This is basically the average number of defective chips, not an actual number. Okay, so this has introduced kind of a new concept here. This is a lot like the indirect method that we've used in the past, where instead of calculating it directly, we take almost like the inverse or the opposite approach and basically calculate the ones that we don't want. Okay. All right, last page. I know this is a bit of a long lesson, but I want to give you guys lots of examples to work from and understand what's going on. This time we're looking at candies. Chocolati Candies Company makes only candy-coated chocolates. 40% are red. The production line mixes the candies randomly and packages 10 per box. Okay, what's the probability that at least 3 candies in a given box are red? So the box has 10. Now they've told us that 40% of the candies are red. They didn't say any other candies, but we don't really need to know. All we need to know is that 40% are red, 60% are not red, because the question is only asking about red. Okay, so let's find that probability. So I have to start off with my random variable x. X will be the number, switch up here, number of red candies in a box of 10. So our probability, they've told us that straight out, the probability of a candy in the box being red is 40%, 0.4. Therefore, the probability that it's not red is 0.6. And our n, in this case, it's a box of 10. So our n is 10. Okay, so we want to know probably at least 3 candies in a given box of red. So you really have to be careful about the wording here. At least 3 basically means 3, 4, 5, 6, 7, 8, 9, 10. So I'm looking for the probability that x, instead of saying x equals 3, 4, 5, 6, 7, 8, 9, 10, I'm going to say x is greater than or equal to 3. I guess I could say greater than 2, since these are going to be discrete values. I can't have 2.5 red candies. Either way, it's going to work out the same here. But I'm trying to use the same number that they did in the description here. So that's going to be equal to, and again, I'm going to use my, for lack of a better word, the indirect method. So instead of calculating the probability that x is 3, x is 4, x is 5, up to x is 10, I'm going to start with 1 and then subtract the probabilities that I don't want, which are probability x equals 0, probability x equals 1, and probability x equals 2. Oops. Okay, so that leaves, so that will take these probabilities out and leave us with the probabilities that x is 3, 4, 5, 6, 7, 8, 9, or 10. Okay, now there's a couple ways you could do this, just to, I'm sure there's people looking at why you're subtracting them all. You could put brackets around the ones you're subtracting and then just add these 3 and then subtract this total from 1. That's fine. I just prefer to subtract them all individually. But either way is good. Okay, so let's, this is very similar to the last question. So we're going to do our probability calculation here. Probability x is 10. So remember, it's n, so it's going to be 10 choose 0, and then 0.4 to the power 0, 0.6 to the power 10. Remember, those two numbers always add up to n. And then we do x for the probability x equals 1. That's going to be 10 choose 1, 0.4 to the power 1, 0.6 to the power 9. 1 plus 9 equals 10. And again, you see the pattern, okay? This number for the combination will always be 10. This number, in this case, it's going up. And it's always going to be the same as that exponent, and then this exponent will be decreasing because the other one is increasing. This will be 10 choose 2, 0.4 to the power 2, 0.6 to the power 8. Okay, so this time I'm just going to put each of these numbers. Okay, so that's 0.0060, quite small, 0.0403, and the last one, it will be 0.1209, and then when I put them together, I get 0.8328. So that's actually quite a high number because the probabilities we're subtracting were all very low. So the probability of having 0, 1, or 2 red candies was very low, looks like 16% or so. So the remaining was boxes that have 3 or more. So conclusion, therefore, probability of at least 3 red candies in a box of 10 is 0.8328. Okay, so hopefully this is becoming a little easier to understand, since we're kind of repeating the types of processes we're doing here. And then the second part, which you're seeing that happens quite a lot, what's the expected number of red candies? So expected number of red candies is, so that's equal to NP, which is 10 times 0.4, which is 4. Okay, and you probably could have answered that just by looking, just by looking at the question. If 40% of the candies are red, what would you expect to find in a box of 10? Well, 10 times 0.4. So makes total sense, hopefully. Last question here. This one's actually, in terms of the calculation, it's quite small, but a couple of things I wanted to bring out here. Again, it sounds like a fairly complicated question. Lots of technology here. A manufacturer of electronic components produces precision resistors designed to have a tolerance of plus or minus 1%. From quality control testing, the manufacturer knows that about 1 resistor in 6 is within 0.3% of its nominal value. A customer needs 3 of these more precise resistors. What's the probability of finding exactly 3 such resistors among the first 5 tested? Okay, so I'm going to make my x random discrete variable, and that is, so I want exactly 3 of these resistors that are within its nominal value. So x is the number of resistors within nominal value. Now let's look at some of the numbers here. Okay, so we want to find 3 of them. So that's basically our value of x that we want. And out of the first 5 tested, well, that's going to be our number of trials. So that's our n value. So x equals 3, n equals 5. Our probability, you kind of have to hunt for that. It says the manufacturer knows that about 1 resistor in 6, so is within the nominal value. So a success happens 1/6 of the time. So that means failure happens 5/6 of the time. Okay, now you notice I've got everything I need at this point, but if you look back in the words, well, we use this, but this plus or minus 1% and this 0.3%. Well, I mean, those were actual information about what's going on, but they have nothing to do with our calculation. Okay, it's more of a descriptive thing about what's considered to be a success or nominal value. And this is an important thing because a lot of students just get totally focused on pulling out numbers and just plugging them in somewhere. So sometimes you get these numbers that could be, they could look like they're important because they're percentages. They look like they might be probabilities, but they're not. You have to read the question. You have to know how to eliminate data that's not really needed for our calculation. So I like this question for that reason, because in most questions, math teachers tend to just give you exactly what you need, nothing more, nothing less, but that's not the real world. So you have to really focus and read the question carefully. I can't stress that enough. So what we're calculating is the probability that x equals 3, because what's the probability of finding exactly 3? So this time it's not a range of values. It's a specific value of x, which means our calculation will be a little smaller. So this is going to be, so n is 5, so it's 5 choose 3, and then our probability is 1/6 to the power 3 times 5/6 to the power, what's left over, 2. Okay, so I'm just going to jump to the answer here, 0.03215. Therefore, there is A. Now, I like to switch back and forth between percent and decimal probabilities, just to make it a little more interesting. So this is 3.215% chance or probability, you could use that word, finding 3 resistors out of 5 within the nominal value. Okay, so that is it for the lesson. Hopefully if we just maybe go back quickly, I don't want to delay this too much more, but I promised we would do this. So there's a definition of binomial distribution. If we read it now, it should make more sense. Specified number of identical independent trials in which the outcome is either success or failure. The probability of success is the same in each trial. So, I mean, every question had a different probability, but probability of the first, second, third pull was exactly the same, as any other. It doesn't change. That's the important thing. Now, here's the probability of X successes in N independent trials. Is this formula. We use that a lot. P is the probability of success. Q is the probability of failure. And the expected value, expectation or expected value for binomial distribution is N times P. Okay, so, and of course you can represent any distribution using a table, histogram, and a formula. So we actually used all 3. This is your probability distribution. This is your histogram from that data. And the formula would be that equation there with the right values of N, X, P, and Q. Okay, so I've got some homework to try this out yourself. It's important to get the practice. And like I said, binomial distribution is very important. The remaining 2 distributions that we're going to be taking in the next 2 lessons, geometric and hypergeometric, are actually related to binomial distribution, but they have a slight twist to them. So that's what we'll be covering in the next 2 lessons. So until then, I hope you have a great day, and we'll see you next time.